So let's talk about atoms. I bet you've got a picture in your head right now of what one looks like. Well, I'm here to tell you that picture, it's wrong. And the reality? Oh, it's so much stranger, so much more elegant, and honestly, way more beautiful than you can possibly imagine. Okay, let's just rip the Band-Aid off right away. You know this image, right? Of course you do. The little solar system with electrons zipping around a nucleus like tiny planets. It's basically the logo for science itself. But it's not an atom, it's an icon, a helpful first step on a long road. But it is not the truth. It's not even close. Now, lie might be a strong word. This model was absolutely crucial in its day. But to really, truly get what an atom is, we have to let this old picture go. So, let's take a quick look at the journey of how we got this image in the first place, and then we'll see why science had to come along and smash it to pieces. You know, for more than 2,000 years, the atom was just an idea, a concept. Then, around the 1800s, scientists started thinking of it as a tiny, hard ball. A little later, we discovered electrons and imagined them stuck inside a positive goo, kind of like plums in a pudding. But the real game changer was Ernest Rutherford. He discovered the nucleus, this tiny, incredibly dense core. And that discovery led Niels Bohr directly to the planetary model in 1913. Yeah, the one we all know and, well, the one we all have to unlearn. This quote from Rutherford just perfectly captures the pure shock that blew up all the old ideas. He was shooting these tiny alpha particles at a super thin sheet of gold foil and figured they'd all just zip right through. But some of them bounced straight back. That was the moment we realized the atom was almost entirely empty space, with a nucleus so dense it could literally stop a particle in its tracks and throw it right back. Okay, so if the planetary model is out, what do we replace it with? What does an atom actually look like? Well, to answer that, we have to leave the comfortable, predictable world of orbits and roads behind and just take a deep dive into the wonderfully weird, probabilistic world of quantum mechanics. First things first, we need a new word. I want you to throw the word orbit out of your vocabulary and replace it with orbital. See, an electron doesn't follow a path like a planet at all. Instead, it kind of exists everywhere within a region of space all at once. This region, this fuzzy cloud of probability, that's the orbital. It's not the electron's house. In a very real way, the cloud is the electron. And here's where it gets really beautiful. These clouds of probability aren't just random shapeless blobs. Oh no, they have precise, stunning geometric shapes. The simplest ones, the s orbitals, are perfect little spheres. Then you get p orbitals, which look like two lobes, like a dumbbell. And as you go on to the d and f orbitals, they bloom into these incredibly complex, gorgeous, flower-like structures. These shapes you see, this is the fundamental architecture of matter itself. This is probably the best way to wrap your head around it. Imagine a moth, right? Fluttering around a streetlight at night. If you take a super fast, instantaneous photo, the moth is in one specific spot. But what if you leave the camera shutter open for a long exposure? You don't see a neat path. You see a blurry, glowing cloud that's brightest near the light. Now here's the key. An electron isn't the moth. The electron is the cloud, a smear of potential existing in all those places at once. So this whole cloud idea builds on what Rutherford found, that the atom is mostly empty space. But it turns out that emptiness, well, it isn't actually empty. In fact, it's the most powerful and important part of the entire atom. You've probably heard this classic analogy. It's great for getting a sense of the scale, the vast distances inside an atom, but it also gives you this false impression of nothingness, as if there's literally just a void between the nucleus and the electron cloud. And that idea leads to a massive paradox. I mean, seriously, think about it for a second. If you're made of atoms that are almost entirely empty, and the floor is made of atoms that are also empty, why is it so solid? Why doesn't your hand just pass straight through your desk? And the answer is that space isn't empty at all. It is buzzing and crackling with invisible but incredibly powerful forces, what we call quantum fields. The so-called vacuum inside an atom is actually a churning, energetic sea of potential. This field is what gives the atom its shape, its structure, and its solidity. Here's a perfect way to picture it. Think of a regular house fan when it's off. The blades themselves are thin, right? There's tons of empty space between them. But turn it on, and suddenly those blades create a solid, impenetrable disk of force. You can't stick your hand through it.
The electron's probability cloud acted exactly like that spinning fan, creating a force field that repels other atoms. That's why the world feels solid.
So, okay, we have this absolutely incredible theory, but how do we know it's really true? I mean, atoms are smaller than the wavelength of visible light. You literally can't see them with a normal microscope, no matter how powerful. So how in the world have we managed to actually get a look at one? Well, one of the most amazing techniques is called phytography. It's kind of like this. Imagine you're in a pitch black room with someone, and you have to figure out what they look like. You can't see them, but you have a million glow-in-the-dark dodgeballs. So you just start throwing them. By watching exactly how the balls bounce and scatter off that person from every possible angle, a powerful computer could reconstruct a perfect image. That's basically what scientists do, but they use a beam of electrons instead of dodgeballs.
Using this method, researchers have captured an image so precise, so unbelievably detailed, it's hard to process that it's real. And I want to be absolutely crystal clear about this. What you are about to see is not a computer model. It's not an artist's rendering.
This is a real photograph of individual atoms. It is the highest resolution picture of atoms ever taken. And you see that slight blurriness around them? That's not a flaw in the image. That is the atoms themselves jiggling and vibrating with their own thermal energy. We are literally seeing what heat looks like at the atomic level. All right, for our last trick, let's connect all of this mind-bending quantum physics to something we can all see and recognize, something that might even be on your finger right now, the color of gold. Have you ever actually stopped to wonder about that? I mean, most metals, silver, aluminum, steel, they just reflect all the colors of light pretty much equally, which is why they look silvery white or gray. But gold is different. It's got that unmistakable warm yellow glow. And the reason for that is one of the coolest stories in all of physics. It all comes down to Einstein's theory of relativity. No, seriously, gold has this massive nucleus, packed with 79 protons. To keep from getting sucked in, its inner electrons have to whip around at more than half the speed of light. Now, according to relativity, anything moving that fast actually gets heavier. This extra mass pulls those electrons in a little closer, which causes a domino effect, making the outer orbitals shrink too. That tiny change is just enough to alter the kind of light the atom absorbs. Gold atoms absorb blue light. And if you take the blue out of white sunlight, what's left to bounce back to your eye is yellow. So let's just step back and look at the incredible journey we've been on. We started by completely tearing down that old, familiar planetary atom. We replaced it with these beautiful, strange clouds of pure probability. We discovered its empty space is actually humming with powerful fields. We looked at a real photograph of atoms jiggling around. And to top it all off, we found out that the color of gold is a direct, visible result of both quantum mechanics and Einstein's theory of relativity working together. This really forces us to change our whole perspective. An atom isn't a static little thing. It's not some tiny object you can point to. It's much more like an event. It's a continuous, dynamic dance of energy, fields, and pure potential. Which, of course, leaves us with one final, pretty mind-bending question. If the solid, stable, predictable world that you can see and touch is built from a foundation of these shimmering, uncertain clouds of pure potential, what does that really say about the nature of reality itself?